Hi, curious people. Robots have been a staple in science fiction for a very long time, but we take for granted that all of these characters can see. Some directors take a crack at what that might look like, but this is very fanciful. Reality, in the end, is a lot more strange. Developers are now enabling that, whether it's Tesla or others, but how does this work? Let's find out together.
Let's start the exploration with this. The digital camera. A CCD or charge-coupled device stands in for the retina in computer vision systems.
This tiny device converts photons which strike its surface into a current. And the chip pulls that current and turns it into a stream of bits and bytes that represent the image. Now, we have to do something with that bit stream to turn it into vision. It's not going to be perception all from go. So let's try to build a cat detector together. The internet's full of cats, so let's see if we can find them. Let's grab a cute image from the internet. Here's a tabby cat, and we'll take a snap of it. Snap. And we need to first break this apart into its constituent colors. All images are made out of red, green, and blue, so let's break those apart, and we'll focus on the green image here. One of the topics that we need to talk about is convolution. It's not totally in vogue anymore, but it's a really important concept for stealing from the retina. The first layer of cells in the retina and the first layer of cells in our vision system, I'm going to try to call out edges by emphasizing the center versus the surround, or reverse. Convolution is an operation we use in telecommunications engineering to mix two signals together. In this case, we're going to use it to combine two matrices together, a small one and a big one, meaning the entire image. And we call the small one the kernel in convolution neural networks. It's what's going to give us that retinal style response. By multiplying across the values in the image and the values in the filter and summing them all up, we get the convolved total. You may notice the number is negative though for the total of the convolution. So what do we do with that? Well, we can use a function called a ReLU, a rectified linear unit, which is really standing in for something much more complicated. It's called a sigmoid, but that's a different story. This allows us to take any result that's below a threshold that we care about and treat it as 0. And if it's above that, if the reaction of the surround in the center is such that we want it to be, we can make it very strong, or even like the full number, 255 in this case. And if we pass that filter across the main image, we'll start to see different responses to that filter.
If the filters are built such that they emphasize the center and downplay the edges, they will have a center-on sensitivity. If we reverse the filter weights, we can get center-off sensitivity, copying that logic in the retina.
You can see what this does on the image of our tabby cat. It pulls out the edges and only shows where there is a contrast. We can do that with both images and superpose them, the center on and the center off. And that's really how the eye is calling out high contrast, and in our model, calling out high contrast as well. And we can do that for all the other colors. So let's take a look at what blue and red also look like with these filters. So that's how one convolution layer works. And that calls out edges like the eye. So if we just stack up layers, is that all we need to create a vision system that can tell cats from not cats across the internet?
We need more layers!
Well, sort of. Let's take a look at some of the quasi-modern networks and see how they work and how many neurons and compute actually takes to see our tabby cat.
To build a cat detector, we need a bunch of labeled images of cats. Huge datasets have already been built to train vision systems such as ImageNet or the COCO dataset, which humans have tediously gone through, highlighting all sorts of features and images. As we look for our feline friends in photos with this detector and continue to train the network, the accuracy will rise.
Ta-da! Here's our tabby cat again, and I've put it into a 3D model of the neural network so we can take a bit of a ride through the neural network. So this yellow and red layers you see here, they're the first convolutions. One feeds into the other, and the weights between them change as we train them. So the filters are learned in this style of network. And in this block, there's actually 64 different pairs of convolutions, making a very large tensor. And because this is VGG16, there are 16 of these types of layers. Here we represented 2, but then there'll also be more as we travel up and get a sense for how large these really are. We can let the layers draw in here, and you'll see that there are 16 different layers. Some of them are max pool, many of them are convolution layers, and at the very end there's this very thin component that you can barely see, which is these dense, fully connected layers that are used to actually call out what is in the image. And a system like this can see about 1,000 different items when it's trained properly. And in our tour of VGG16, we end up at the beginning again, at the very start of the first convolutions. So that's the network, and hopefully you get a sense of like how large this really is. But I also decided to test this with this actual image. So let's give it a try and see what the result is. Bang! A tabby cat. It actually works.
The bigger the network 2 that we can run, the better it will detect and perceive cats. Inception ResNet 164, more layers each time, better performance. Sort of. These systems are large enough to find objects like cats, but they do have flaws. Unfortunately, we can't actually grow the network forever to get a perfect result. A large convolution neural net will diminish its performance as the stack grows. There are neat tricks that deep learning developers have learned. For example, ResNets fix this by essentially passing a residual of the data stream up from a lower level to a higher level in the stacks. This allows what I'm going to call the coherence of the neural network to remain more stable than it would if you simply just stacked layers on top, feeding one network or one input into the next.
So let's recap. That's really a bit of a rundown of what computer vision looked like before the last 2 years. Convolution neural nets can be built into a very large stack which can perceive a tabby cat by changing some weights and running some convolutions. But there's a limit to that, as I just said, and that won't work forever. So there's something else called a transformer, which is all the rage through ChatGPT and Bard and everything you've heard about large language models. And there's also a way to make that work for vision and live video.
Which is a big step forward. Why process information you don't need? That's not relevant to the function of the system. Why are you looking at grass when you need to find cats? The transformer allows the neural network to pull out the most prominent feature of the data stream without human labeling. By leveraging transformers in the visual domain, we can start doing something called unsupervised self-labeling. There is a system being tested right now by MIT called STEGO, which stands for Self-Supervised Transformer with Energy-Based Graph Optimization. A mouthful, but STEGO learns by something called semantic segmentation, like looking at every pixel and giving it its pixels its own labels by itself. This semantic segmentation is an important building block to having a computer system pull apart visual images or input data and map those commonalities between those images on its own. It's something that you do on the fly. And it's a big step towards a more biological learning style. Pay attention to certain things, observe the world, and then learn those things. Despite those improvements though, STEGO still faces certain challenges. While it tries to form its own understanding of relevant features and images, it still must align what it understands or sees with a large labeled data set. For example, the human-made labels of the Cocoa Stuff dataset have overlapping categories. Food things, like bananas and chicken wings, and food stuff, like grits and pasta. STEGO and many humans don't see any nuance between those categories.
Transformers are the current state of the art. Whether we're talking large language models or vision, they are what's driving AI technology today. And hopefully this video helps you understand where the technology was and how it works and leads into what we're using today, and maybe gives you a couple ideas of where that will go in the future.
In short, to start perceiving lines, shapes, organisms, buildings, or writing, we can stack up convolution layers and then train them to see what we want. In our example, cats. Modern deep learning networks need labeled data to start that training process, and they need some sort of reinforcement mechanism to retrain themselves. They run, test, fail, train, and repeat. In the next series of videos, we'll dig deeper into humans versus machine perception, behavior. We'll start some hardcore experiments into the pie car. As well, we'll need to build a cluster computer to power it. Keep creating, and see you soon.